Number 1, state the zeros of the function given by f of x equals negative x plus 5 times x plus 1 times x minus 2. Sketch a graph of this function. So to find the zeros, I'm going to figure out when does this function equal 0. And luckily, this polynomial is already in factored form, because once it's in factored form, we can apply the zero product property because it's set equal to 0. So there's really a negative 1. Does negative 1 ever equal 0? No. So we get x equals negative 5, x equals negative 1, and x equals 2. Those are my three zeros. How can I use those to graph this function? Well, I know the function is going to hit the x-axis at those points. At negative 5, I'm going to hit the x-axis. At negative 1, I'm going to hit the x-axis. And positive 2, I'm going to hit the x-axis. We're just sketching a graph here, so we don't need to look at a table really. We just want to get the overall picture of the graph of this function. So let's go to your graphing calculator. I'm going to go to Desmos to do this because it looks nicer. Here's the overall shape of this polynomial. It has a 0 at negative 5, negative 2, and 1, just like we expected. So I'm going to sketch a graph of that. The function starts up here, hits negative 5, turns around, and goes back down there at negative 2. That's a sketch of the function of f of x. What are the solutions to f of x equals 0? Well, that's saying what are the zeros of the function? We already found those. That's x equals negative 5, x equals negative 1, and x equals 2. If I take those values and substitute them in for x, we get the same. We get 0 equals 0. So the solutions are the same thing as the zeros of this function. Number 2. Algebraically determine the zeros of this function. So I want to know when does this function equal 0? And to solve a polynomial equation, we want it set equal to 0, check, and we want it in factored form. So I have 3 terms here. I have 4 terms here. It's a cubic polynomial, so I need to use grouping. Factor out the GCF of both of the terms, and we get x squared times x minus 2 minus 1 times x minus 2. I'm going to factor out the GCF of x minus 2, and I'm left with x squared minus 1. But I know that x squared minus 1 is the difference of perfect squares. So when is it equal to 0? At x equals 2, x equals negative 1, and x equals positive 1. So on my graph, I know it's going to hit the x-axis at those points, at 2, at 1, and at negative 1. I'm going to go to Desmos, or you can go to your TI-84, and I'm going to graph this function to see what it should look like. So after graphing this function, we see it has this cubic-like behavior, and I have zeros at negative 1, 1, and 2. So let's go back and sketch what that function looks like. It starts at negative infinity. Don't want it dotted. It starts at negative infinity, hits the x-axis, turns around again, and then goes off to infinity. So that's a sketch of the graph of f of x. Label the relative maximum and minimum points on your sketch. So we don't know what these points actually are. We need calculus to do that, so we have to wait a couple years before you can actually find the maximums and minimums, but that's a relative max, that's a relative min. If you really want to know what they are, Desmos will tell us what they are. Your TI-84 will not. There's the relative max, there's the relative min. Great. The key thing is that that's where the function reaches the highest point in that little area around it. Number 3, let f of x equal x times x plus 1 squared times x minus 1 squared. Graph this function on your calculator. State the zeros, state the solutions to f of x equals 0, and state the x-intercepts. So let's graph this function. So I graph that function on my TI-84, and I see the behavior of this graph here. Where does this function have zeros? Well, there's one at negative 1, there's one at 0, and there's one at positive 1. If we wanted to check, we could look at the table. So if we had second graph, where does it hit 0? At negative 1, 0, and positive 1. So state the zeros of this function. Well, we could have determined this algebraically and said x equals 0, x equals negative 1. That has a 0 of multiplicity too, because that's a repeated root. and x equals positive 1, that has multiplicity too, because that's also a repeated factor. Those are the zeros. What are the solutions to this equation f of x equals 0? Well, when does that function equal 0? Well, at x equals 1, x equals negative 1, and x equals 1. What are the x-intercepts? Where does this function cross the x-axis? At x equals 0, x equals negative 1, and x equals 1. The zeros, the solutions, and the x-intercept, the solutions to f of x equals 0, are all the same thing. There are three different ways to ask, when does the function hit the x-axis? When does the function output a 0? Number 4, write an equation of a degree 4 polynomial that only has x-intercepts at x equals 5 and x equals negative 3 in factored form. So this uses the factor 0 theorem. If I have an x-intercept at x equals 5, well, what factor did that come from? That came from a factor of x minus 5. If x equals negative 3 is a 0, that came from a factor of x plus 3. So my function is p of x equals x minus 5 times x plus 3. But I want a degree 4 polynomial. So right now this is only a degree 2 polynomial, because if I multiplied this together, I'd get a quadratic. So you have options here. You could say, well, maybe I have 3x minus 5 factors. Maybe it has a repeated, that has a multiplicity of 3. Now I have a degree 4 polynomial. Or you could say, well, maybe I have a repeated x minus 5 factor and an x plus 3 factor is also repeated. That also gives me a degree 4 polynomial. Or maybe you like both of those but want to have a leading coefficient. Having a leading coefficient doesn't change the degree of the polynomial. And the last case that I could possibly think of is you add a factor that doesn't have any solution, any x-intercepts. So if you add something like x squared plus 1, x squared plus 1 doesn't have any x-intercepts. So you've created a degree 4 polynomial that still only has those two x-intercepts. Either of these functions is correct. You could add any leading coefficient that you want, but it has to be a degree 4. The highest power after I multiply it out would have to be x to the 4th. Number 5, let f of x be x minus 1 times x plus 3 squared, and g of x be x minus 1 times x plus 3 cubed. State the zeros of both functions and their zeros' multiplicity. Describe the effect of a root with an even multiplicity has on the graph of the polynomial. So first let's find the zeros. First let's find the zeros and say, when does f of x equal to 0? Well, that's when x minus 1 times x plus 3 squared is equal to 0. Using the zero product property, we get x equals 1 and x equals negative 3. The multiplicities tells me how many times, the multiplicity of a 0 is how many times is that 0 a factor. Well, that has a multiplicity of 1 because I only have a factor of x minus 1. But x equals negative 3 is a repeated root because I have two factors of x plus 3, so that has a multiplicity of 2. For g of x, we have the same zeros, because we still have the same factors, x equals 1 and x equals negative 3. X equals 1 still has a multiplicity of 1, because there's only one factor of x minus 1, but x equals negative 3 has a multiplicity of 3 because x plus 3, there's 3 of those factors. So the multiplicity is just how many times does that 0 occur. So we have to describe the effect of a root with an even multiplicity has on the graph of the polynomial. So let's graph both of these and explore what effect changing the multiplicity, changing how many times x plus 3 is a factor, has on the effect of on the graph. So I graph both of the functions. F of x is the green function, f of x is the green function, and the purple function is when x plus 3 is a factor 3 times. Notice how both of these functions still have the only zeros at x equals negative 3 and x equals negative 1. So let me only look at the green function. Notice how this function hits the x-axis at x equals negative 3, but then turns around, but then passes through when x equals 1. So because that has that even multiplicity, it has an even multiplicity of 2, it hits the x-axis and then turns around. Let's look at the purple function now. X equals negative 3, it has an odd multiplicity again, so it passes through, and then it passes through at x equals 1. So the key thing to take away from this is if it has an even multiplicity, like the green function does here, f of x does, it hits the x-axis, and then it turns around, and doesn't cross through it like it would if it had an odd multiplicity, like x minus 1 does in both of these functions. So the key thing that we want to summarize from this question is even multiplicities cause the function to hit the 0, to touch the x-axis. It's tangent to the x-axis, but then it turns around. Odd multiplicities cross through. Cross through the x-axis. Okay, even multiplicities touch it and turn around. Odd multiplicities cross through. This is an important concept to understand for when we start graphing functions with just graphing a sketch of them without using a calculator. Number 6, if you forgot how to factor a polynomial, explain how you can use the graph of the polynomial to help you factor it. Well, what we can do is we can graph it. Let's graph the polynomial and look at its zeros. Look at the x-intercepts. And then we can apply the factor zero theorem. So if we see that it has zeros at x equals 5 and x equals negative 3, I know the factors are x minus 5. One of the factors is x minus 5, and another factor is x plus 3. What this doesn't account for, though, is it doesn't account for repeated roots, and it also doesn't account for leading coefficients. Maybe there's a leading coefficient in the original polynomial that you lose once you factor it. So it's not a fail-proof way, but it's a good way to check your work is to graph the polynomial and see, do my zeros match the zeros that I would get from my factors? So it's a powerful tool to say, wait a minute, if I graph this, I see that x equals negative 3 is a 0, which means that x plus 3 is a factor. So it's using the factor zero theorem with your calculator doing most of the work. Number 7, solve the equation for all real values of x. State the multiplicity of each zero. So, polynomial equation solving, I want it set equal to 0. It is. If not, we would have to collect the terms on one side. Now, because this looks ridiculous and all these things are being multiplied together, I'm going to apply the zero product property now instead of factoring it. But normally you would factor. But the zero product property says if I multiply a bunch of things together and get 0, one of those things has to be 0. So x equals 0, great. X squared minus 36 equals 0. 2x squared minus 11x minus 6 equals 0, or x cubed plus 6x squared minus 4x minus 24 equals 0. X equals 0, we're done. This is the difference of perfect squares, x plus 6, x minus 6 equals 0. So I have solutions of x equals negative 6 and x equals positive 6. I have to factor this trinomial, but this is a trinomial with a leading coefficient. So I'm going to want to use the add multiply. The AC method, not the add multiply rule, the AC method. What multiplies to a times c? What multiplies to negative 12 that adds to negative 11? What are the factors of negative 12 that add to negative 11? Well, negative 12 and 1. So I get 2x squared minus 12x plus 1x minus 6. Factor out my GCF now by grouping. Get x minus 6. I want to factor out a 1, so I get an x minus 6 over there. So this factors into x minus 6 times 2x plus 1. So x equals 6, or 2x plus 1 equals 0, which means subtract the 1, 2x equals negative 1, or x equals negative a half. And finally, I have to factor this cubic polynomial here. There's 4 terms, so I'm going to have to group. Factor out an x squared and get x plus 6. Factor out a negative 4 and get x plus 6. So that gives me x plus 6 times, what am I left with? X squared minus 4. X squared minus 4 is the difference of perfect squares. So I get x minus 2, x plus 2. So we get x equals negative 6, x equals positive 2, and x equals negative 2 after we use the zero product property. So what are my zeros? My zeros are x equals 0, x equals negative 6, x equals positive 6, x equals negative a half, x equals 2, and x equals negative 2. Notice that x equals 6 is a repeated 0, so that has a multiplicity of 2. X equals negative 6 is a repeated 0, so that has a multiplicity of 2 as well. All the other values, all the other zeros have a multiplicity of 1, because there's only one of them here. Number 8, factor. So, I see the minus sign, so it's probably the difference of perfect squares or the difference of perfect cubes. X cubed is a clear giveaway that this is the difference of perfect cubes. What's in the front seat? 3x cubed is 27x cubed. Minus 5y squared cubed is 125y to the 6th. So, this factors as 3x minus 5y squared, same sign, times the first thing squared, which is 9x squared, opposite sign, multiply these two together. 3 times 5 is 15, xy squared, always positive, the last term squared gives me 25y to the 4th. Just reviewing the differences and sums of perfect cubes. 9. If x plus 3 is a factor of that polynomial, factor it completely. So I'm telling you that x plus 3 is a factor. What that means is that if I divide that polynomial by x plus 3, I'll find the other term that multiplied by x plus 3 gives me that polynomial. So go through and run long division. If you like reverse tabular, feel free to use reverse tabular. Subtract. To subtract, I change the signs. I'm going to bring the other terms down and repeat the process. What times x gives me minus 13x squared? Well, minus 13x. Minus 13x squared, minus 39x. Change the signs. Those add to 0. 4x plus 12. What times x gives me 4x? Well, plus 4. This looks good because I get a remainder of 0. Remember, something is only a factor if you have a remainder of 0. If you have a remainder of anything else, it's not a factor. So, what this tells me is that 3x cubed minus 4x squared minus 35x plus 12 equals x plus 3 times the quotient, 3x squared minus 13x plus 4. But I want it factored completely. So, look at that trinomial. How do I factor trinomials with a leading coefficient? The AC method. What multiplies to a times c? What multiplies to 12? That adds to negative 13. Stop for a minute and think about that. Pause the video if you need to. You get negative 12, negative 1. So, I have 3x squared minus 12x minus 1x plus 4. Factor out of 3x. I'm going to group now and get x minus 4. Factor out a negative 1 and get x minus 4. So, that polynomial factors into x minus 4 was my GCF down there, and I'm left with 3x minus 1. So, factoring completely, that cubic polynomial is equal to the product of those three binomials. Key thing to take away is if I give you a factor, you can simplify it, you can partially factor it by going through that long division process. Remainders of 0 are good because it means it's a factor. Number 10, if f of 4 equals negative 4. I'm going to stop right there. This is function notation. F of 4 means when x equals 4, my y is negative 4. So this function passes through the point 4, negative 4. When I plug in a 4, I get out a negative 4. Here is f of x. Here's the function that we're talking about. Find the value of c. Find this unknown value for c. So if I plug in x equals 4, I should get out negative 4. So 4 cubed plus 4 squared plus 4 times c, so plus 4c minus 4, has to equal negative 4. Lots of 4's going on here. 4 cubed is 64, plus 16, plus 4c minus 4. Combine my like terms over here. I get 80 minus 4 is minus 76 plus 4c. Solve for c. This is just a nice simple linear equation. I'm going to, that's a positive 76. That's a positive 76 because 64 plus 16 is 80 minus 4 is positive 76. Subtract that 76 over. Negative 80 equals 4c. Well, I don't care about 4c. I want plain old c. They're being multiplied together, so I'm going to divide by 4 and get c equals negative 20. So the value of c that makes the function pass through that point is negative 20. So f of x is x cubed plus x squared minus 20x minus 4.